bunch of excellent questions, and I can imagine there's a lot more that could be asked, and hopefully there'll be some more discussion. Okay, so our last presentation of this section is Samantha Oliver. She was USGS, and she's going to be talking about how machine learning, KGML is being used in the USGS or in federal government.
I'll start talking while Anuj sets up. Thanks for inviting me. I'm going to talk today about how KGML is being used in the USGS. Specifically, you've heard a lot of examples this morning, and a lot of these water temperature use cases came from a collaboration between the USGS and the University of Minnesota. So I'm excited to talk about it today. And I won't hide that this is a sales pitch to come work with the USGS or for the USGS, because we benefit a lot from these KGML collaborations. Thank you. All right, so I'm briefly going to talk about how this collaboration started, and then I'm going to talk about a few USGS prediction problems and how we benefit from KGML. I'm not going to spend a ton of time on that, although our benefits are great. I'm going to talk mostly about what USGS can bring to the KGML space to get you to call us up and help us solve our problems. Okay, so how did it all start? This has been referenced a lot today, but we originally were in the business of lake temperature water predictions, and we use process-based models to do that. And Jake talked a little bit about the general lake model. Oh, let's see, no focus for me. And we have a lot of information, but when you build a process-based model, and particularly when you want to do that for thousands of lakes across the landscape, it is very hard to fully use all of the data that you have available to you, because essentially that would take calibrating individual GLM models for all of those thousands of lakes across the landscape. And so, we were parameterizing these models with things like lake depth and lake size, but we actually weren't using the observations to calibrate individual lake models. And so that left a lot to be gained in terms of predictive performance. And so there was this need to improve performance so that we could do things like estimate cold water habitat across the landscape for fish. And so that was when we partnered with the University of Minnesota in this KGML space. And it has been said many times, we introduced or brought in theory into machine learning models in a variety of different ways. And this is just telling you more of what's already been said. But this collaboration led to many, many more problem spaces being solved with KGML, everything from extreme water temperature prediction, solving how to make predictions in rivers, and it's been a really fruitful collaboration. So I hope I can convince you today to collaborate with the USGS for advancing KGML. Okay, so kind of the mission of the USGS Water Mission Area, which is where I work. We work with our partners to monitor, assess, conduct targeted research, and deliver information on a wide range of water resource issues, including streamflow, groundwater, water quality, and water use and availability. That's a big statement, but there are lots of very specific questions that are baked into that statement that we try to answer for our partners. And we're often trying to do this at really large spatial scales. So I just wanted to give you a few examples of some of the questions that the USGS is trying to answer so that you can see yourself in those questions. So if someone wants to drill a new well, will that impact stream flow at X location? Which basins in the United States contribute the most nitrogen to the Gulf of Mexico, and therefore where should we focus our conservation efforts? How much surface and groundwater is being used by bottled water facilities? Is flood frequency changing? Do we need to change our 100-year flood maps? Where will algal toxins impact water availability for drinking water? These are really important societal questions. They need to be solved at large spatial extents, and they range in complexity from simple water temperature questions that we know the thermodynamics well to algal toxin production, which I would argue we know very, very little about. So there's lots of places for KGML to enter the USGS problem space, and we have benefited greatly by collaborating. The other reason we benefit greatly is because it is really hard for us to attract and retain the talent that it takes to implement KGML in the USGS. Some parts of the federal government are better at this, but I would argue that the approaches that the USGS takes largely reflect the scientists that we employ, and those are mostly hydrologists, not computer scientists. Although this is changing, and I would argue it's changing because of our collaborations and that we've shown how useful it is to have computer scientists working on these problems. But we build process-based models a lot. We do not build KGML models a lot, and I think that's just a reflection of our workforce. And so collaborating with computer scientists really expands the tools that we have in our toolkit. So this is a really important mechanism for us to be able to stay on the cutting edge. And I wanted to provide a really concrete example of kind of the difference between how a USGS hydrologist would approach a USGS problem compared to how collaboration with a computer scientist would look in solving that same problem. And so this problem is one that Jake sort of described, but when we're predicting stream temperature on a stream network, it is not just stream processes that are important for determining stream temperature. We also have to consider the embedded reservoirs that are in that network that kind of change the relationship between the weather patterns and the temperature that you're observing. And that is because reservoirs slow down the water and allow for heat storage. And a lot of these reservoirs are putting out water from the bottom water that's very cold. And so it just kind of breaks up the temperature dynamics of the stream network that you need to account for. So how would a hydrologist solve this? In a really convoluted way is the answer, or was our answer. We took two process-based models because the way that we choose models is not based on what model works best, it's on what models we know. We took two process-based models, a stream temperature process-based model, a reservoir or lake temperature model, and we statistically combined them and said, basically, the further downriver you are from a reservoir, the less influence you will see from that reservoir. It's not a bad approach. It worked. It improved accuracy. But it's kind of intensive in terms of what you need to spin up to accomplish those predictions. You need two process-based modelers who know each of those models, someone to bring them together. And then it is very, very reservoir specific. It is not generalizable. Alternatively, you can just partner with Zhao Wei and Vipin and their groups, and they will come up with elegant mathematical solutions and representations in their architectures to solve the same problem. And so in this case, they came up with this heterogeneous graph network. And this was really elegant because essentially it treated nodes in the model differently based on what we knew them to be, either rivers or reservoirs. And it allowed us to provide unique inputs into each of those nodes. Inputs are drivers. So you could include static features of the reservoirs, like dam height, storage capacity, to predict the reservoir dynamics. And then you could put things like stream width into the stream nodes. And this is a really flexible, generalizable approach. It's much less intensive in terms of the data needed for each individual reservoir stream node. And so it's a really elegant solution to the same problem. And I guarantee that we would never have come up with that on our own. So this is just highlighting the benefit of this collaboration. Okay, so what can USGS bring to you all? This is where my sales pitch starts. Um, this is our latest water cycle diagram that was just redesigned by folks in the water mission area. And it's beautiful, but it also kind of represents what I think is our collective knowledge in the USGS. Each of those boxes is representing an ecosystem. The arrows are reflecting process or movement. And I would say for each of those boxes or each of those arrows, there are probably dozens of hydrologists that just study that box or that arrow. And there are probably dozens of mechanistic or process-based models that the USGS has developed in each of those boxes and in each of those arrows. So collectively, I think what we bring to the table is a lot of domain expertise and a lot of models that you can think about how you can use in this KGML landscape to insert knowledge into machine or deep learning. We also bring a lot of real world use cases, demands from the government, from the people, and we are trying to answer specific questions about water availability. So the USGS is working on a national water census. The eventual goal is for real-time, routinely updated, nationally consistent modeled water quantity, quality, and use. We cannot get there alone. That is a big, big challenge. And we will use that information to make assessments of water availability for the nation. So I've heard this described as like the IPCC report for water. And this is really exciting to me. This is kind of a roadmap for the United States water decision making. And I hope that you're excited to contribute to those use cases. Oh, shoot, my pretty little image isn't showing in the background. I'm even going to delete it just so you can see it. We also provide a lot of data. As Charu mentioned, this isn't probably going to work for me to do. That's okay. Oh, there we go. We bring a lot of data to the table. So we have those supporting data sets, but we also have thousands of USGS gauges on the landscape collecting real-time data. And this figure is just showing each blue dot is a gauge relative to the population distribution in the United States. You can probably walk, bike, or drive to a USGS gauge no matter where you are in the country within 15 minutes. And this is providing, each of those dots is kind of representing a unique societal need. That gauge is there because of flooding issues, because of drinking water issues, because of water quality issues. And so we bring a lot of data to the table. We're collecting more information every day. And the great thing, Charu mentioned data quality. The USGS gauge network is collected, in a consistent way, a consistent format, delivered on a consistent platform. And so this can really be kind of baseline or foundational data for the community to build on. And as Jake and Charu mentioned, we also provide a lot of supporting data like the gauges 2 information for each of those dots. It's providing contextual data to support modeling efforts. And there are many products in the USGS like that that can help support these modeling efforts and drive some of this methods development and really important questions like how complex does a model have to be? And then something else that's been mentioned quite a bit today is how can we trust these models? And I think something that the USGS brings is devotion to this question, because we are often in the space of having to convince someone to trust the information that we're putting out there. And so we spend a lot of time thinking about this. And I think the reason is because we fundamentally do not trust these models. We are skeptics. We are hydrologists that can't possibly believe that static watershed characteristics don't matter. That is like built into our core. And so we're always looking for ways to kind of show how these models are working. Can we trust these models? Can we use these models to answer the very specific questions that our stakeholders have? So the figure on the left is this paper by Simon Top, where he was showing whether or not we could use these recurrent neural graph networks to make projections into the future. And he did this nice experiment where he's showing the prediction attribution across the stream network and showing, you might not want to believe a model that's using information 100 miles downstream to make a projection into the future. That information might be useful to making a more accurate prediction, but you can imagine all of the ways that that might go wrong if you're projecting out into the future. And so I highly recommend Simon's paper to spur some thinking and some thinking on experiments that we can all do to make sure that we trust these models for the questions at hand. And then this other image, this little GIF is showing you this kind of explainer that we put together after we had been working with Zhao for a long time and Vipin's group. We don't understand neural networks. And so having to explain them to other people forces us to find ways to describe them in plain language and plain images. And so this website that we built, How We Model Temperature in the Delaware River Basin, we really took a lot of time to describe what is a neural network, what is process guidance, so that our community, both hydrologists and the users of our information, could understand and trust what we're doing. And so I think we bring this, can we trust these models, to the forefront of some of these questions, and is something that we can bring to these collaborations. So that's all I'm going to say. So I think the USGS benefits greatly from these collaborations by bringing computer scientists to the table, expanding the tools that we have in this toolkit. The models that come out of KGML tend to be more flexible, accurate, scalable, and quicker, not just computationally, but sometimes we feel like we can't give you data fast enough because you are spinning models up so quickly that it's a great feedback loop for us. What we bring to the KGML collaborations are complex but societally relevant problems to solve. We bring our domain expertise, our process understanding, and our models. And we have lots of environmental data to support those methods development. And we hope together we can build trust in these models. Thank you.
Few minutes to ask some questions. Yeah.
Thank you for the great talk. I have a question about the water quality you just mentioned a couple of times. Does USGS do some process model trying to establish the machine learning to predict the pollution, water pollution?
Yes and no. We do have process-based models that start to get us towards water quality predictions. Temperature is one of those examples, but for something like nitrogen, phosphorus, there are often parts of that we have a good process-based understanding of, like runoff processes that are transporting sediment, for example. But even when we do have process-based models, there are a lot of empirically derived parameters in those models. So water quality is certainly a space, thinking about Jake's framework, where are we in terms of data? The data is also expensive and hard to get, but the theory is not completely there either. So water quality, nutrients, biogeochemistry is, I think, an interesting space for KGML.
Thank you so much. Your recruitment talk is successful, so I'm very convinced.
Great.
I also very excited you bring up this particular perspective on building trust among the experts, between experts and also the machine learning model. I guess for us that we have a very long history of trying to do so, but whenever I generate these interpretations or whenever I show some approximating linear functions that I think the experts were looking at the interpretation were like, no, well, that's nice. And then they just left. So I wonder, like, for example, when you have the process model, right? That is the traditional models, simulations that you were building using these physics knowledge or other type of knowledge. How did the experts gaining trust from these systems? So in the sense that we can learn from them so that we can know, oh, what is the right process to actually gaining the trust?
Yeah, I don't have the answer to that, but I can talk a little bit about the ways that I've seen people build trust. I think we as humans like anecdotes, and even as data scientists, as hydrologists. And so often I see people like, can we recreate a specific event that people know about, that we experience? Like, I know that 2018 flooded my street. Can we recreate that 2018 flood? And so even in this collaboration space, whenever we would get model results from the computer scientists, they'd send a table of like root mean squared error or whatever. And I'd be like, oh, hey, can you plot up like a summertime time series from this one place below a reservoir? Because I know that's really hard to predict. And so I think metrics are really important, and to think about as a community, like what will make us trust a model beyond accuracy. And to me, that's a lot of like visual representation of results, a lot of specific examples of how the model is recreating something that in our head we think is really complex and hard to capture. So I think that's one lesson to take away from this collaboration.
Thank you, Sam. I think that we are going to take a 5-minute break right now, and we're well behind schedule. So, but 5-minute break, and then we'll come back.
But this was a great discussion. Lots of great questions, and this is what it's all about. So this has been a fascinating session. Yeah, we'll start in 5 minutes. Yeah, thank you.